Hello, this is Teach Nichols, and this lecture is on the parts of a circuit and how to draw circuit diagrams. The essential question is, what are the critical parts of every circuit, and how do I represent them in a scientifically recognizable drawing? Some of this may be familiar with you from ninth grade physics or from other hobbies, so review as needed. So there are a few critical elements that every circuit will have. Number one, it has to have a source of energy. Number two, it has to have a resistor, sometimes called a load, or the thing that takes that energy from the energy source and turns it into something else useful. Like, this is the point of the circuit. The reason we plug things into batteries, into wall sockets, is to get something to do something. Third thing it needs to have is some sort of connective wire, and then sometimes circuits have switches. A quick note, every single part of the circuit starts with electrons. There is one in every, for every proton in every atom. So circuits are electrically neutral. The point of a circuit is not to create electrons or destroy them. It's just to move them around and with them the energy that they carry. So the function of the energy source is to do work on the existing electrons by pushing them together in one part of the circuit, right? That adds electrical potential energy to every single electron because they don't want to be piled up in one part of the circuit. Some examples of energy sources: batteries, sometimes called cells. The wall outlet, of course, is an energy source. A solar panel could be an energy source, or a generator. When you represent these things in drawings, we don't usually want to draw the physical object. It's simpler to have a shorthand way of representing them. Batteries or cells are typically drawn like this. You can see wire coming out of the top and the bottom, and those two parallel lines are the battery. There will be one longer than the other. The longer side is the positive end of the battery. Of course, that means the electrons are actually piled up or pushed out of the other end of the battery in reality. Another sort of energy source is a capacitor. Capacitors are interesting because they are not creating their own energy. You have to use another energy source to basically charge them up, to fill their plates with charges. But once they are charged, they can do the same thing batteries do, which is basically push electrons through the circuit. So capacitors are drawn similar to a battery, except for the two sides are the same length. Which one of those plates becomes positive and which one becomes negative depends on the energy source that you hook up to charge up the capacitor in the first place. As I mentioned at the beginning, the resistor or the load is the element in the circuit that transforms the electrical energy. So for example, light bulbs or toasters or electric motors, that thing that I showed right there is a plain old resistor. Its job is just to sort of waste energy in a circuit, and we'll talk about why we need those later on, but you may have seen that before if you've looked inside of any kind of circuit boards. This is a dimmer switch, which you've probably seen on the wall, which is actually not a switch. It's actually a resistor, and we'll talk about that in a minute as well. When you draw resistors in circuits, this is the safest way to draw them. Really, in my opinion, most resistors can be drawn this way. It's just a series of zigzag lines that kind of show the electrons as they go through that location. They're going to be losing their electrical potential energy, turning it into something else. Light bulbs, which are a kind of resistor, sometimes are drawn as plain old resistors, but other times there may be special symbols that show that this resistor is specifically a light bulb. Sometimes you see this X thing, and sometimes you see this kind of like roller coaster situation. Those are both schematic light bulbs. An LED is a kind of light source as well. We've been getting a lot more of those recently. You probably can think of lots of devices that have LED bulbs, but they're drawn differently. They actually are drawn with a triangle and a line on the end of that triangle, so that is specifically an LED bulb. Those two little arrows coming out sort of are representative of the light that comes out of LED bulbs. Some resistors are called variable resistors, and these resistors are things that you can actually adjust. You can change the resistance using some sort of slider or a dial. We'll talk about how those work specifically in a future lecture. Sometimes they are referred to in problems as potentiometers. That's probably the technical name for them, or sometimes just a dimmer switch. So any of those things mean basically a resistor whose value, whose resistance can be changed manually. When those are drawn in circuits, they usually look like this, which is like a plain old resistor, but then that line through the middle indicates that the value is not set, but can shift upwards or downwards depending on the user. The wire is the conductive material that is going to make a circuit complete. So the idea is that you have to have a complete circle or loop from the energy source to the resistor and then back again to the energy source for the electrons to move. We'll talk about two different categories of wires as we move through this unit. If it's not said otherwise, we assume wires are quote unquote ideal. And this is like a wire that has no resistance. That means that the length of it, the dimensions, the material it's made out of don't matter. It's considered to be a perfect conductor and allows electrons to flow without any energy loss. In the real world, that doesn't actually exist, and we'll talk about how to sort of characterize real wires in a future lecture. But generally speaking, they will tell you if the wire is not to be considered ideal. Examples of things that can be wires, mostly wires, copper wires. Of course, if you happen to touch two parts of a circuit and a very high energy source, sometimes a person can act as a wire as well because we are also conductive. In circuit diagrams, wires are represented just with plain lines that connect one part of the circuit to the other. Switches and buttons are important parts of circuits because they can be used to disconnect or connect wires in different orientations. A wire that is broken is called an open switch because it's like an open door, and that means the electrons cannot flow across that gap. If the switch is in this orientation, that's known as a closed switch, and that is basically connecting the two ends of the wire so that electrons could move. Some examples of switches: light switches, power buttons, circuit breakers if you've ever been in the electrical panel of your house. On a circuit diagram, usually switches are kind of drawn as open by default, and you discuss different how the closing of that switch would impact the devices that are in the circuit. So a switch is basically drawn like a little door. And an important note is that if you want electrons to move in your circuit, there has to be a closed loop that allows those electrons to return to the battery. Switches in that same vein can be used to control or change which devices are getting that flow of electrons and which ones are not. So in this circuit diagram shown below, you'll notice switches 2 and 3 and 1. Like 1, if 1 is open, nothing is on in the circuit because electrons can't get back to the battery, so nothing is going to move. But if 1 is closed, then we can use switch 2 and 3 to determine what is happening with those other light bulbs. So if 3 is closed, then 2 of the light bulbs are on, but the light bulb in the middle would not be on because 2 is open, not allowing electrons to go through. So this is a little bit logic puzzly as you use those switches to determine what components of the circuit would be active. So the word circuit diagram just refers to combining all of these components into a single meaningful diagram, as I showed in the last page. This would be what it really actually looks like, right? Squiggly wires mostly connecting things, an actual battery connected to a bulb. But if you were going to draw a circuit diagram, you would likely make it nice and clean. If we assume all those wires are ideal, this is exactly the same situation in terms of analysis, in terms of physics, well, I guess except for the switch there. But in any case, this circuit diagram essentially represents the same physics as happening in the picture above. If you've ever actually tried to do some wiring in your house, you know it's actually really sort of complicated and messy. So we don't actually try to draw the way it looks like in the walls. We're going to simplify things with these nice, square, clean circuit diagrams. So most of the rest of the earlier part of the video should have been kind of review from 9th grade physics. But now I want to talk about, like, from a deeper level, what is really actually happening in a circuit at an atomic level. This is kind of like also a summary preview of what's going to be going on for the rest of the unit. The first thing that was mentioned that I'm repeating is that the electrons exist already in every atom in the wire, battery, and resistor. Okay. Generally, every element in a circuit is a conductor, which means the electrons are able to flow or move from one place to the other. Important fact number one, no electrons are created or destroyed as they move through the circuit. That's going to end up being just one of the guiding principles for explaining what is happening in circuits. You've got to be able to track all of your electrons. We can't lose any, and we can't create any electrons from the moment they leave the battery till they come back. The power source in the circuit, which is the battery in this diagram, is going to energize the electrons by essentially pumping them in one direction. So it uses its energy. Batteries use chemical energy. Other power sources use different kinds of energy to force those electrons into closer proximity, which increases their electric potential energy per electron, which is the voltage. So batteries actually tell you voltage when you look at them, which is basically how much energy per electron or per coulomb of electrons can I force those electrons to have by my pumping action. So batteries have characteristic voltage values that depend on the chemical reactions that are occurring inside of them. If the switch is closed, then those electrons that are all piled up on one side of the battery are going to see an opportunity to go through conductors and return to a spot in the battery that does not have piled up electrons, right? That's what every electron wants, is to go from a place where there's too many electrons to a place where there's not enough electrons. So closing the switch allows those electrons to have a conducting path back to the other side of the battery, at which point, of course, the battery pumps them back to the point where they started and the cycle repeats itself. In the process of moving from one side of the battery to the other, the resistors are the components that the electrons must go through. As the electrons go through those resistors, they are going to transform their energy that they start with into some other kind of energy, which means that the spacing between the electrons changes when we are going through the resistor. So we are piled up on one side of the resistor and then spread out or less piled up on the other, because we have lost energy in that resistor. That energy has turned into something else, and therefore the spacing changes from one side to the other. Another way to look at that is a negative delta V. So the batteries added voltage or added energy to the electrons. When they go through the resistors, they are going to be losing some of that voltage or transforming it into other types. A point about that, electrons have to use all of their electric energy before they return to the battery to start the cycle again. This is a manifestation of conservation of energy, but another way to phrase it is that the overall delta V for any loop in any circuit is going to be 0. So as much energy as we gain in the battery, we must lose all of that energy in the resistors before we return to the battery. So this is kind of what is happening in circuits at an atomic level. Okay, let's take a minute and revisit the essential question, which was, what are the critical parts of a circuit? How do I represent them in a drawing? And I'm going to leave you with the Calvin and Hobbes. Thanks for watching.